Thinking Aloud. Conversations on the leading edge of knowledge and discovery with psychologist Jeffrey Mishlove.
Hello and welcome. I'm Jeffrey Mishlove. This is part 3 of our 6-part series on consciousness in the brain with Professor Stuart Hameroff of the Banner University Medical Center at the University of Arizona, where he is a professor of anesthesiology and psychology and author of Ultimate Computing, Biomolecular Consciousness and Nanotechnology. He is also the co-founder of the Center for Consciousness Studies and the organizer of the annual Toward a Science of Consciousness conference that's been held since 1994 at the University of Arizona. Welcome again, Stuart.
Thank you, Jeffrey.
With Sir Roger Penrose, you developed the Orch OR theory of consciousness, which is a very comprehensive model integrating the mysterious world of quantum physics with not only brain physiology, but also conscious experience. Let's talk about how you got into that approach.
Well, I had been interested in these structures called microtubules inside neurons for many years, since the early 70s.
Yes.
And I was going around to meetings of artificial intelligence and people, and neural net people, who were trying to model the brain based on the idea that each neuron was a simple on-off switch, a bit. And there are about 100 billion neurons in the brain that can switch 1,000 times a second at about 100 hertz, or 1,000 synapses at 100 hertz, giving about 10 to the 16th operations per second. And I had calculated...
That's a big number.
That's a very big number. And they say the singularity people, for example, Ray Kurzweil, say that when this number is reached in a computer, when you can have 10 to the 16th operations per second, we'll have brain equivalents, including consciousness. And that's kind of an assumption underlying artificial intelligence.
Now, when they use the word singularity in that way, they mean that this will be an earth-shattering event. I mean, singularity is a word that's sometimes associated with the Big Bang, an event of significance almost at that level.
Yes, they claim it will change everything. It would be a paradigm shift. Computers will become more intelligent, but although what intelligence means is another issue, and have consciousness. And some people warn about that they could take over. There's lots of sci-fi about that, the Skynet and the Terminator movies, for example, and many, many others. This has been going on for many, many years.
Sure.
But I was going around in the 80s to these meetings saying, your goal is not the real goal, because if you consider what biological organisms can do in terms of processing information at a lower level in the microtubules, you get this number about 10 to the 16th operations per second in each and every neuron. So you would at least have to multiply it times the number of neurons, 10 to the 11th, to get something like 10 to the 27th operations per second, which pushed their goal way downstream, and so I wasn't very popular among those.
In other words, you're saying the brain is about 1 trillion times more powerful than they thought it was, just in terms of information processing.
Yes, exactly. And as I said, I wasn't very popular, but then one day somebody said to me, well, let's say you're right, let's say there's all this information processing. How would that explain consciousness? How would that explain love, joy, emotion, envy, feelings, pain, blueness, what philosophers came to call qualia? And this became known as the hard problem. Subjective experience as opposed to computation. They're not necessarily the same. The artificial intelligence folks have always assumed that when you get to this level of computational complexity, a critical level, that consciousness would emerge magically, it seems, out of computational complexity. And this guy was turning that around and saying the same thing to me, that how would that explain consciousness? And it kind of stunned me for a second, more than a second. I realized I'd become a reductionist and really didn't have an answer. How would that explain consciousness? Well, fortunately, that person recommended that I read a book by Sir Roger Penrose called The Emperor's New Mind. And the Emperor was probably meant to be Marvin Minsky, who was the scion of AI at that time. But the point was that AI was really bluffing, that they really didn't have anything to relate to consciousness.
Well, we need to make a careful distinction between intelligence and consciousness, don't we?
Absolutely. There are machines now. My laptop is more intelligent than me in a lot of ways, and computers can beat the best chess players in the world in chess. But as Roger pointed out, they don't understand anything. Using Gödel's theorem, a philosophical mathematical argument, he showed that understanding is lacking in computation. Computation can do a lot of things, but there's no understanding. And John Searle had a similar argument called the Chinese room argument. If you put somebody in a room and with a lookup table that this Chinese character means this, he can make this translation, and he could literally translate things into Chinese or out of Chinese, but without understanding Chinese. So these types of arguments show that consciousness is more than computation. And in this book, which kind of blew me away, it was fantastic, broad-ranging over many, many areas with lots of really cool illustrations, hand-drawn illustrations by Roger. He offered a solution to what was missing. If it's not computation, what is it? He claimed that there was some other ingredient, that there was something non-computable in understanding, or as well as in feeling and conscious awareness and emotion and so forth, something that came, and this was the real mind-blowing thing, something that came from quantum physics, a particular type of collapse of the wave function. And he related it to the structure of the universe. So back in the early 90s when I read this, I was quite literally blown away.
Now let's step back for just a moment and talk about who Sir Roger Penrose is. He really made a reputation for himself with his theorizing about the nature of black holes.
He and Stephen Hawking really developed the theory of black holes. And the Big Bang and general relativity and mathematics and a lot of quantum physics and geometry. At his heart, Roger is a mathematical physicist interested in geometry, in form. And he's particularly interested in Platonic forms. You know, Plato said that the law of the good, that geometric forms really represent information and represent everything. And Roger thought that these forms were actually intrinsic to the universe, built into the fine-scale structure of reality. And that came out of his book, but he also related it to a problem called collapse of the wave function, or the measurement problem.
But now let me just slow down a minute and unpack what you just said, because it's quite profound. In other words, Roger Penrose was a Platonist.
Among other things, yes.
A Platonist as opposed to a reductionist.
Correct.
A Platonist who believes that embedded in the very essence of the universe are Platonic forms, including mathematical ideas, and also including aesthetic and ethical ideas, so that one might say that these elements of consciousness are not separate from the universe, but part of its very essence.
That is correct. I think of it now as kind of a resonance, so that when we have a conscious thought and are mindful about it and make a decision that maybe feels right, it's because we're in resonance with the structure of the universe at a deeper level. It took me many years to actually put it in those terms. It was a little bit more difficult at that time. But the first thing that I had to deal with was quantum physics, which I had pretty much ignored for most of my career up to that point.
It's not normally something that anesthesiologists and psychologists deal with.
Or neuroscientists, or many other fields. But if you're a physicist, it's something that you should know about. And what I came to understand, and I'll just tell you in my terms, is that the world is sort of divided into two realms. And in our large scale meaning our scale, roughly, everyday world, things are fairly predictable. They follow Newton's laws of motion, the electromagnetic laws of Maxwell, the gas laws, and a bunch of other laws. And things are predictable, and things work out pretty well. And in the late 19th century, physicists thought, well, we've got everything pretty much figured out. But there were two glitches. One was a funny thing in the orbit of Mercury, which led to general relativity, and black body radiation, which showed that energy radiated was quantized, came in discrete packets. And so what it boils down to, I think, is that at small scales, so at large scales, everything works pretty well. At small scales, everything is crazy. Okay, if you go down below a certain level, and the problem is we don't know the level. It seems to vary.
But there seems to be a threshold somewhere.
Some kind of boundary, some kind of edge, and below that boundary, below that edge, the laws of quantum mechanics reign. And the laws of quantum mechanics are completely different. For example, in quantum mechanics, if you have a particle, a quantum particle, it can be in one place, it can vibrate to another place, back and forth, or it can exist in two places at the same time. This is called quantum superposition. It can be at two places or two states at the same time. If it's a spin, it can be spin up and spin down at the same time. It can be in two places, two states at the same time. So quantum superposition, things get smeared out, act more like a wave than a particle.
Totally defying Aristotelian logic.
Totally defying classical physics, yes. Another strange phenomenon is entanglement. So if you have a particle, two particles that are in superposition but complementary. So for example, two electrons, and if one is spin up, this one has to be spin down. So they can both be in superposition, spin up and spin down, but they're still complementary. If you then, and Einstein posed this thought experiment, because the laws of quantum mechanics would seem to say that they would be connected no matter what, no matter
how far apart they might be.
Right. So Einstein, Podolsky, and Rosen, so this is called EPR, came up with a thought experiment that said, okay, if you take one of these particles, superposition particles that's complementary, and send it that way, and 100 miles, and take this one and send it 100 miles that way, they're 200 miles apart. If you make a measurement over here and this one's up, this one instantaneously should be down. And Einstein...
Instantaneously, meaning faster than the speed of light.
Correct, which Einstein didn't like, because his special relativity said that the speed of light was an absolute. You could not exceed it. And so he posed this thought experiment as to show how silly, how ludicrous was the idea of this non-locality.
He hoped to disprove quantum physics by virtue of that thought experiment.
Exactly. He was putting relativity against quantum against quantum physics.
As I recall, he said, if this is true, why, it means there are ghosts.
He also said it would be spooky action at a distance.
Spooky action at a distance.
And so he didn't like the idea. So the thought experiment was put forth in 1935. In 1985, the experiment was done by Alan Aspect in Paris. And sure enough, it worked. They sent a superposition particle over here. It was just across the lab, so a few meters away, and went over here and made a measurement here. This one instantaneously was the opposite.
They were, even though it was in the same lab, they could tell it was faster than the speed of light.
Well, it was instantaneous.
Instantaneous.
Yeah.
And I know John Clauser at Berkeley conducted similar experiments.
The experiment is done in various ways, hundreds of thousands of times since. In fact, this non-local entanglement, it's called, quantum entanglement, is the basis for quantum teleportation, which is used in technology, quantum computing, and quantum cryptography, which is the basis for a lot of military and banking codes. Because if you use this, if somebody eavesdrops, you know it. So it's a very secure method of coding and cryptography. But it raised the specter of non-locality. That's the things can be connected over distance instantaneously.
Yes.
And it's still a mystery. Even though it's used, it's still a mystery. The third mysterious feature of quantum mechanics was condensation or coherence. That if you had quantum particles, they could condense and behave as if they were one. So if you had a bunch of atoms or molecules or ions or spin states, they could condense and all be in one state. And if you perturbed any one of them, any of the others would feel it. It's as if they were literally connected. So this is condensation or coherence, quantum coherence. So these are the main features. The biggest problem initially was, why don't we see superpositions in our real world? We don't see things in two places at once or smeared out.
Right.
Niels Bohr, who was one of the pioneers of quantum mechanics, was doing experiments around the turn of the 20th century, and this problem came up because it seemed as though they would have a quantum system, they would make a measurement of it with a machine, and the results, it appeared, even in the machine, would stay in superposition of multiple possibilities until a human observer looked at the results. And Wigner and John von Neumann and others came up with the idea, well, consciousness causes collapse of the wave function.
Now, you're referring to some of the great names of 20th century physics.
Absolutely. Bohr, Eugene Wigner, John von Neumann, and then Schrödinger.
These are the founders of quantum theory who are already talking about consciousness having an impact in the quantum world.
They had to bring in consciousness to make sense of quantum physics. Now, Schrödinger thought the conscious observer was ludicrous. So he came up with another thought experiment called Schrodinger's cat. And it dealt with the issue of how large a quantum system could become, still be in two states at the same time. So what he said was, imagine a cat in a box with a vial of poison, and outside the box you have a quantum superposition state. Let's say a photon going through a half-silvered mirror. So the photon will both go through the mirror and be reflected by the mirror, because it's a quantum particle. If it is reflected, it will enter the box, trigger the poison, and kill the cat. Now, he said, according to the Copenhagen interpretation, it became known as the observer effect because of Bohr's Danish origin. He said, according to the conscious observer effect, the cat will be both dead and alive until someone opens the box and takes a look.
Yes.
That's the party line that they were taking, the conscious observer effect. And so you had the specter of a cat both dead and alive until somebody opened the box. So Schrodinger intended that as he put it, a burlesque example of how ludicrous was this approach.
Yes.
And it certainly is, but it also, nobody's really solved the problem. We don't know how large a quantum system can become. Now, there's problems with the cat. It's got its own consciousness and so forth and so on. But we still don't know how large a quantum system can become and why we don't see superpositions in our real world. Now, there's a number of...
but there is a threshold, as we pointed out earlier. At some amount of mass or size, things stop behaving like quantum particles.
That's one view, and that's called the objective reduction view, where there's an objective threshold that causes quantum state reduction or collapse.
Penrose's view, I believe.
This is Penrose's view. There are other objective reduction views, like the number of particles, the GRW theory, and the Hungarians, Diassi and Caroli, Hazy, and others had similar ideas related to Rogers, but they all basically said there's some threshold, and the Penrose is related to the structure of the universe. But the more popular views, besides the observer effect, are decoherence, that any interaction with a classical world will disrupt it. But that would rule out any quantum system of any kind. Another is multiple worlds. The multiple worlds hypothesis says that a superposition means that the universe itself separates, that maybe the space-time geometry separates, and each possibility will branch off and form its own universe. And we have this infinite number of overlapping multiple universes. And that's actually a very popular view, multiple worlds, multiverse, and so forth. Now, Penrose came along, and what he did in his book, The Emperor's New Mind, which I think is one of the most brilliant, but he did it in cartoon form, which made it easy to understand, and later in mathematical form. He said that he brought in Einstein's general relativity. Now, Einstein equated mass with curvature in space-time geometry.
Yes.
And so, for example, he said the sun, being a hugely massive object, will bend light, will disturb space-time, its big curvature in space-time, so that light behind the sun would actually curve and be visible through the sun.
And that's been confirmed.
That was confirmed in 1929 by Sir Arthur Eddington. Now, he needed an eclipse so he could see something near the sun. So he went to a mountaintop for a particular eclipse of the sun, and sure enough, observed a star that he knew would be behind the sun. He could see it at its edge because the curvature of space-time due to the mass of the sun was curving space-time, the space-time metric, and he could see it. So that verified Einstein's theory of general relativity. Now, Penrose came along and said, yes, for massive objects like the sun, you have very large curvatures.
Yes. Small
particles would have small curvatures. So what he said, and I think this is really profound, that a particle over here is like a little tiny, like let's say an atom, is a little tiny curvature in space-time geometry. And a particle, if it moves over here, it's a curvature in another direction. Now, if it's in superposition, if it's both here and here, you have a curvature this way, and you have a curvature this way, which means it's a separation in space-time geometry. This is very similar to the multiple worlds hypothesis, because you have two curvatures in you're separating, and you have a separation in underlying structure of the universe.
These are curvatures in space itself.
curvatures of space-time geometry. Yeah, this is tricky because this is space-time.
Yes.
So it's not existing in anything.
Yeah.
It gets complicated. Roger calls it a symplectic measure, and it gets into very dense mathematics. But it's basically a separation in the structure of the universe. And were these to continue, you'd have multiple worlds. If these separations continued, you could see this particle will form its own universe over here, and this particle would form its own universe over there. Penrose said, no, these separations are unstable and will reduce or self-collapse after a certain time t. And the time t would be determined by the amount of mass in superposition with the amount of space-time curvature. So a large mass in superposition would collapse or reduce very quickly. It's E equals h over t, a very simple equation where E is the amount of the superposition, h is Planck's constant, which gets you into the quantum realm, and t the time of collapse.
Okay.
So a large mass would collapse very quickly. A small mass would take a long time. For an example, an electron in superposition, assuming you could leave it alone and isolate it, would take about 10 million years to reach threshold and self-collapse. And where a large, like Schrodinger's cat, which is a kilogram, let's say, would be something like 10 to the minus 30 seconds. It would happen so fast you wouldn't notice it. So it solved that problem.
So that's an explanation of why the classical world we view through our senses does not behave like quantum reality.
It's an example of why we don't see superpositions.
Okay.
Because they either, but the kicker was that he said when these collapses occur by E equals h over t, a moment of subjective experience accompanies it. That a moment of consciousness occurs. You could think of it as being emitted, or kind of, I think of sometimes as fluorescence when a excited electron drops off and emits a photon. So whenever these objective reductions occur, you get a moment of conscious experience by this simple equation E equals h over t.
Now, but let me ask you this question, is because we earlier said that Penrose is not a reductionist, and yet it sounds as if you're saying that consciousness is somehow reduced to this objective reduction.
You could say, well, you could say that it's an identity theory. In other words, when this reduction occurs, that is consciousness.
That is consciousness.
That is consciousness. And philosophers don't like identity theories because, for a lot of reasons, but so they object to this. Because some people have claimed, well, neural firing is consciousness. That's an identity theory, which really doesn't make any sense. But he reduces it to this objective reduction by this quantum gravity, because the curvature is really related to quantum gravity, giving rise to consciousness. The other kicker was that the choices of this state or that state were not random. Now, in other interpretations of the measurement problem, it's called, the choices would be random. So, for example, if you have decoherence, it would be the choice of which state it would reduce to would be random. And in the measurement and the observer, if you believe that conscious observation causes it, the choice of whether the cat would be dead or alive would be random, like flipping a coin. But Penrose said that no, when this occurs, there's a non-computable influence coming from Platonic values embedded in the fine-scale structure of the universe. This was the part that really threw me for a loop. Because to me, this implied so many things that could relate to spirituality, to deeper meaning, and really give meaning to life. Because he was saying, as I understood it, that there are Platonic values, as you said before, good, aesthetic, ethical, not only mathematical truth, but also qualia, perceptions, consciousness, that are intrinsic features of the universe, and that if we're mindful and allow our thoughts to be guided by them, then they can influence our thoughts. So if and our perception, so you do something because it feels right, or it's intuitive, or it's instinct, or something, you may be actually being influenced by these Platonic values embedded in the fine-scale structure of the universe.
Or one might, for purposes of simplicity, say that there's a wisdom inherent in the universe itself that we can partake of.
Freeman Dyson has said similar things. Yes, that there's a cosmic intelligence, something like that.
Freeman Dyson being another physicist.
Another very famous physicist. Yes, yes. So this, to me, brought all kinds of things together, including, as I said, spirituality. Although Roger doesn't like to talk about it. But in any case, reading this book back in 1990 or so, I thought, wow, this guy is brilliant. And I don't understand a lot of this, but it feels right. It's intuitive, and above all, he's got a mechanism for consciousness.
Yes.
And I had studied consciousness for 20, 25 years at that time, and I had never heard anybody put forth a specific mechanism, an identity for consciousness, other than ones that just didn't make any sense for various reasons. So I thought, wow, he's got a mechanism, but he doesn't have the structure. And he said it in the book. He didn't have a structure for a quantum computer that could self-collapse. Maybe neurons firing and not firing a superposition. But he knew, and I knew that those were large scale. So I thought, wow, microtubules are what he needs. Microtubules, because they have this quantum channel pi resonance internal core, could be quantum devices. They're small enough to be influenced by quantum states. They're at the deeper level in neurons. And so I suggested to him that microtubules were his structure and his objective reduction was my mechanism, and so we teamed up.
And that's the basis of your collaboration and the development of the Orch OR theory of consciousness.
Yes, it is.
Stuart Hameroff, thank you so much for being with me. It's been a pleasure to share with you this wonderful, amazing journey.
Thank you, Jeffrey.
And thank you for being with us. Don't forget to check your channel listings for part 4 of our 6-part series on consciousness and the brain with Professor Stuart Hameroff.